All right, so in your math class, you probably spent some time dealing with second-order polynomial equations, they're called. They'd often in math class be written something like this, maybe. Y as a function of x looks like ax squared plus bx plus c. The reason it's called a second-order polynomial is that the independent variable on the right-hand side, the x, is raised to the second power. And you probably learned several methods for solving these types of equations, notably the quadratic formula, which is very useful. But what I want to just take a look at now is understanding and making sure we see the connection between the way this is written and our one-dimensional equation of motion, which again we saw was x equals x naught plus v naught t plus 1/2 at squared. And so all this is now, the equation of motion, this is just a second-order polynomial with the independent variable of t. Okay, we could write on the left-hand side, just to make this symmetry a little more obvious, x as a function of t. Okay, and so now you should be used to dealing with second-order polynomials and basically their graphs and what they would look like if we were to plot them. We can do a couple simple ones here. For example, if I wanted to plot x versus t on a little axis, I could write my axes like this. That's a vertical x-axis and a horizontal time axis. And now let's say, for example, I had a situation with 0 acceleration. So a equals 0, v naught equals some initial velocity, and let's say x naught also equals 0. So this tells us some of these terms that we would put into here. Our equation of motion would then look like this: x equals 0 plus v naught t plus 0. All I did was take these zeros and put them in there and simplify to that. And now we have a linear line, right? If I were to plot it on this graph, it would look something like this, just a straight line. And this is the motion graph for an object undergoing a constant velocity. It's just a straight line. Another situation that I could imagine would be one where maybe I had a non-zero acceleration. So let's say acceleration equals a. The initial velocity, now let's call that equal to 0, and the initial position is equal to 0. If I substitute all of these into the equation of motion, then I get something that looks like this. X equals 0 plus 0 plus 1/2 at squared, which simplifies to x equals 1/2 at squared. And now that, if I tried to plot that, that would look just like a simple parabola opening upward, right? Something kind of like this. And so there we have a motion graph for an object experiencing a constant positive acceleration given an initial velocity of 0 and initial position also of 0. Okay, and so really critical thing here is to realize that this one-dimensional equation of motion is nothing other than a second-order polynomial. Each of these terms maps to one of these math coefficients. This is how we talk about it in math class. This is how we do it in physics class. So I can see my c term is essentially just x naught. The b term is basically equivalent to the initial velocity, and my a term in the math version is equal to 1/2 acceleration. Okay, and so all the tools you use to evaluate this in math class, you can just transfer them now to physics class. And by doing so, you'll make Galileo very happy.